Good morning, everyone. Welcome to Life Sciences Grade 12. My name is Dutuzile Kupega. We are still on the topic of evolution by natural selection. So this is where we finished off yesterday, where we were looking at the theory of ontogeny repeats phylogeny, which basically means that the development of an individual, it repeats the same process that the development of a species goes through. And you can see that proof over here, whereby these embryos over here, especially in this stage, they are all literally, they're very, very similar. Their structures are very, very similar. You can't even tell which one is a human being, which one is a rabbit, which one is a cat. They're all very similar, and which one is a fish. And only when they are grown can you start to notice the differences. So that's the theory of ontogeny recapitulates phylogeny. So we were discussing this when we were discussing the evidence for evolution. Another evidence is what is anatomy. Darwin said that organisms undergo changes in order to adapt to the environment. If all mammals developed from a common ancestor, they should have certain characteristics in common. If we look at the forelimbs of a number of mammals, we can see a striking resemblance. So you can look at the forelimbs, then we'll see that striking resemblance. Many of the same skeletal elements make up the forelimbs of the humans, cats, whales, bats, as can be seen in activity 3. I'll show you that activity I did included here. You can see the anatomy, the human, cats, whales, and bats, especially in those forelimbs. Although these appendages may have different functions, so of course they are similar, yes, when you look at the structure, but in different organisms, they might have different functions. For example, a whale's flipper is used for swimming, whereby a bat's wing is used for flying. You see, although the structure is quite similar, it is used for different functions in the different organisms or species. But they have what? Those characteristics are similar. This means that they could have shared an unknown common ancestor. Similarity in characteristics arising from known common features is known as homology. So whenever you're asked about homology, it's the similarity in characteristics arising from known features. That is called what? Homology. These forelimbs are called homologous structures arising from their strongly visible similar features or characteristics. So I'll show you the activity here today, whereby we can look at the different forelimbs of these different organisms and see how similar they are. And then vertical structures. Many organisms have organs or structures that seem to be unnecessary since they do not have a clear function. These are thought to be possible remnants, which are the remainders of more developed structures that were essential in their ancestral organisms. The wings of an ostrich, for example. You look at the wings of the ostrich doesn't fly, yet it has those wings. Ne? Birds' wings are complex anatomical structures adapted for flight. So birds, all birds, their wings are adapted for flight. But ostriches cannot use their wings to fly. Ostriches, you wouldn't find an ostrich flying. These wings are vestigial wings, meaning that an ancestor of the modern ostrich could fly some time long ago. The vestigial wings of an ostrich are used for functions such as balance during running or courtship displays during mating. And in the human body, there are a number of vestigial structures. For example, the appendix. We don't really know what the appendix is for. It's just there. So the evolution suspect it might have to do with the fact that our ancestors probably had used the structures like a vestigial structure. It was a feature, a very useful feature in the ancestors we had. The coccyx as well, which is the fused tailbones, and the muscles that move our ears, possibly even our little toes are vestigial. So These are a lot of things we are that and they are vestigial in human beings. So we can study different organisms and look at which features are vestigial in those in organisms. It's basically features they have but don't really use. So it's suspected that then it probably they belonged to their ancestor. Here, look at the why are the wings of ostriches, penguins, and the extinct dodo considered vestigial structures. Why are they considered vestigial structures? Because they have them, even though they're a common feature in other species similar to them for flying, for example. These organisms don't fly, so it's figured that their ancestor probably used them for flight, but now these organisms or these species that we have today don't use them. And then this activity here, we won't, of course, this activity, you'll see how it's set up. We won't be able to do it online. It is, what was Archaeopteryx, the Archaeopteryx. What you need for this activity, if you can do it at home or at schools, I'm pretty sure you'll do it in school. The following information, what you need, the following information, which is the photograph of an Archaeopteryx fossil and drawing. So a photograph and a drawing. What you do, you need to study the photograph on the right, which shows the fossil of Archaeopteryx, an organism which scientists believed lived about 150 million years ago. So this is an organism that lived about 150 million years ago. Then you answer the following questions. The questions will guide you to make a decision on whether this organism is a bird, a reptile, or a transitional organism. You are strongly advised to consult other sources, which are reference books and the internet, to find more information on Archaeopteryx. So think of this, please do this. It would help you understand the topic much better. Then you design a poster with the title, The Reptile Bird. So why? What was the Archaeopteryx? Remember, we need to consult other sources. Getting this evidence can be tricky at this stage, so we will simply speculate, guys. You can literally you can go through other sources as well on the internet or different books as well as your own individual work. Although Archaeopteryx had feathers, we are not sure whether they were used for regulating its body temperature or for flight. So we're not sure. They had feathers, yes, but we're not sure if they were for body temperature or for flight. Scientists are still debating this issue. Feathers may have originally evolved for insulation and only later became co-opted for flight. Also, although we commonly associate feathers with birds, a small theropod dinosaur fossil, which was called the Sinosauropteryx, was discovered in China in 1996. It had what appeared to be feathers preserved along the back. So when you see an organism with feathers, you'd first assume it's a bird, right? You'd assume that. But all that was that reasoning or that information that we know and have always known was disrupted by the discovery of this organism, the fossil of this dinosaur in China. When they found the fossil of this dinosaur, it appeared that it had feathers which were preserved along its back. So now it proves that not only birds have feathers, dinosaurs as well, and possibly other organisms could have had beards, could have had feathers, I mean. So remember, what we needed is that picture of the Archaeopteryx as well as a drawing of the Archaeopteryx. Here's a drawing of this here. So when you look at this, what does it look like to you? Does it look like a bird or a reptile? Ne? Questions. Question 1. Scientists and artists tried to develop a model of what Archaeopteryx looked like. This image here, B. By studying the fossil evidence in A. So they studied this fossil evidence here, which is A. Whenever I say A, I'm referring to this one. They studied the fossil evidence here, and then they made up this drawing over here. This here is a model, then the question 1 is a model always an accurate reflection of reality. So you see, based on this fossil, this was the original and the real one. They found this fossil. But this drawing here was just a drawing made to try and determine exactly what the original organism actually looked like. So this is the model that was then drawn. So question 1 is asking if a model is always an accurate reflection of reality. And you need to explain that. Now, models play a central role in life sciences. And in just general sciences, we have models for different things. We have models for the double helix DNA, you know, that's a model. We have models for that. Scientists spend a great deal of time building, testing, comparing, and revising models. So it is, we cannot definitely say it's 100% reflection of reality. But what is done is whatever fossils are found or whatever evidence is found, that is tried, that information is put together into a model so that we can get a physical or a practical view of what that could look like in its physical form. So it's based on research, it's based on information given, but we cannot say it's 100% accurate, particularly for this one. We can't really say that, but it is pretty close to being real. So as the more evidence we found, the more research we find, it's more likely to change our view of what we know. So the models, like we say, they're always tested, compared, and revised because it's not always 100% accurate. We can't really be sure, especially if we've never seen the thing. We've never seen the archaeopteryx. We've never seen it. No one has seen it. They've just seen the fossil records of it. So that's why with each new information coming up, it is being tested, it's compared, and it's revised. So it's continuously getting improved. Maybe one day, if possible, we could find the whole information surrounding that. But yeah, things like that, like dinosaurs, it's constantly being modeled so that we can try and work out what it looked like. And then question 2, what reptile-like characteristics do you see in the Archaeopteryx? What bird-like characteristics do you see in the Archaeopteryx? You might find it useful to revise the characteristics of birds and reptiles. These ones were covered in grade 11, ne? But let's just look through here. When avian or bird-like characteristics is feathers, the big toes, which is the opposable hallux, then the wishbone, which is formed of 2 clavicles, and then the pubis elongated and directed backwards. So those are basic characteristics of birds that we see on the Archaeopteryx here. It has wings, the big toe there, as well as wishbone formed of 2 clavicles, the pubis. Then reptile-like characteristics. Reptiles, they did not have a bill. The trunk region vertebrae are free, long bony tail, and maxilla red teeth. So those are reptile-like characteristics, avian-like characteristics. So those ones are seen, can be seen. When you remember, you need to consult other studies as well. When you see this Archaeopteryx and you do your further study, these are the common features that are seen here. So it has characteristics of birds as well as characteristics of reptiles. That's why we are calling it right now, we are calling it the bird reptile. Yeah, we don't know for sure. And then, yeah, then you would do your own research. This I'm giving it to you. Would you classify this as a bird or a reptile? So it's based on your personal opinion. What do you think? Based on your research, of course, you'll conduct research. What do you think this is? What would you classify it as? Would you classify it as a bird or a reptile? And then, could this organism, the Archaeopteryx, be a common ancestor for birds and reptiles? Could it then maybe be that it's a common ancestor for both these species, and these two, like the birds and the reptiles, emerged from this one common ancestor? Because if we can't classify it as one, chances are it was just the common ancestor, and then the two, which is the birds and the reptiles, maybe this one, the Archaeopteryx, then the birds and the reptiles emerged from it. So that's also a possibility you can explore. Is it possible that it happened like that? And then, could the Archaeopteryx perhaps be seen as the first bird evolving from reptiles? So you can maybe say it was a reptile first. No, it's a reptile, and then there were reptiles. Then the Archaeopteryx emerged from those reptiles to become the first bird that emerged from reptiles. So though you can explore various options, there can be various possibilities. So conduct your research and then email them to me when you're done. And then this is activity 3. You saw here when we're speaking of homology. There now. Your teacher, again, this is supposed to be a practical task in class or even as homework, so you can do it as homework. Your teacher will provide you with a large illustration similar to the one on the right, scissors and colored pens or pencils, which are Koki pens, and a notebook. So you need those. And I'll provide you with, we'll see that diagram with these different images or structures. So you need such, ne? And if I can even when if you need this, I can even email it to you. Formulate a hypothesis, whereby when you're formulating an hypothesis, it's like being confronted with a sealed box containing an unknown object and being asked to figure out what is in the box. You'll make certain observations. Direct observations will include what you can see, feel, or smell. You may also make indirect observations. If we use the example of the box with the object in it, you can twist the box around and listen to the object inside the box. By listening to the sound it makes, you can tell whether it is a jagged or a smooth surface. Once a scientist has made certain observations, he or she will formulate a hypothesis to assist in making meaning of the observations. A hypothesis is like an educated guess. And after you have studied the bones of the different mammals, you need to formulate a hypothesis. So we're going to look at what at homology, trying to prove how, as it's stated here, what is homology and how does it provide evidence for the process of change? Remember we said we will study different structures of different organisms and see which structures they have in common and how then the similarities in those characteristics of those structures prove or show that they serve as evidence of evolution. After you have studied the hypothesis, like we said, it's an educated guess. And that's a very important thing you need to understand. You don't just make a guess. It needs to be educated. It needs to be informed by certain things. The reason you would make such a guess. You can't just guess things from nowhere and you can't even try and back it up. You can't even try and test whatever theory. When you provide a hypothesis, you need to be willing to also test it, but you can't just make it up. Like I can't just say dogs can fly. Clear how it's not educated at all. You've never seen a dog fly. So what exactly informed this guess that you have? It needs to be an informed guess. It's an educated guess. So I can't just say that such things which you yourselves have never even seen. You haven't even been informed by that. You understand? It's things you have observed and then maybe the trend you've seen from your observations, you put it forth as your hypothesis. And after you have studied the bones of the different mammals, you will need to formulate hypothesis. So I'll show you a diagram where we look at the different bones of the mammals, then we'll make a hypothesis. So this here you can find in the Via Africa Life Sciences book, the learner's book, so you can see more of the instructions and try and do it at home. Then you can color in. There's also the diagram there. You can color in. I can provide it for you to you as well if you can email it to me on our website. And then after you've done this for the forelimbs, which is color in, you'll color in the humerus, purple, different colors for the different structures. After you are done, you will cut the bones out and make sure you do not mix up the bones of different species. Then you will compare the different forelimb bones of the different organisms by designing your own tables. So you can do that. That's on your own. These are the questions now that follow that activity. Question 1. What do these bones tell us about the similarities and differences between these animals? After you're done with this, you'll see the bones. Then you can see that the bones here, they tell you that the same skeletal elements make up the forelimbs of humans, cats, whales, and bats. Although these appendages may have different functions, they have similar characteristics. That's what you'll deduce. You can even just Google search online to find this information. I'll show you the bones just now. And then what do these bones tell us about their possible origin? They probably all developed over millions of years from a single common ancestor. That's what we can say for a fact. That's why, chances are that's why they are so similar. It's because they've come from the same ancestor. Question 3, what do these bones tell us about the adaptations which occurred in the animals for them to survive in the environments in which they are found? What do they tell us about the adaptations that occurred so that they can survive in the organisms, in the environments they are in? You see the ones we are comparing here, it's the human, the cat, whales, and bats. Those ones are all living, except for cats and humans, they are all living in similar environments, you understand? But the whale lives in a different environment, and then the bat functions quite differently from humans and cats. So what does it tell us about the adaptations? A whale's flipper became adapted for swimming. Whale's flipper became adapted for swimming. A cat's paws and claws for hunting and climbing. Remember, when you speak of cat, it's not just the small pet cat you have, it's other cats, all cats actually, the big cats, all of them. So the paws and their claws, they became adapted for hunting and climbing. Whereas that of the whale, it became adapted for swimming, the flipper. But a bat's wing was adapted for flying, and a human's arms and fingers for a range of activity as a bipedal organism, e.g., when we get food, making and manipulating tools, to also hold onto things, when you try and hold on, when you hold the handle, door handle, things like that, we've become adapted to those things. And all of those are different characteristics, so different adaptations, but they were necessary because these organisms are all need to survive in different ways because of how we are structured. But they originated from the same similar structured bones. That's the thing. It was the same bones, but when they develop in these different organisms, they are there for different functions. Then here, these are the homologous structures we are speaking about that you would need to color in. You look at the humerus. Let me just try highlight the humerus so it can be clear. Let's look at the humerus here. This is the human humerus. Then this is the cat's humerus. You see, these structures are the same. It's literally the same bone in different organisms. This here, the humerus in whales, though, it's like this, but you see it's a similar structure. Similar, not the same, 100% the same, just similar. Then this one for the bat over here. Just these two, we can look at that. We can also compare the ulna. Let me try a different color for the ulna. Let's take the green or the orange. Green is fine. I'm trying to color in the ulna. It won't be very nice coloring in. There's the ulna there. There's the ulna here. There's the ulna here. You see again, similar structures. Ulna here. You see, this one here, the one for the bat, has merged with the humerus. But anyway, these structures are quite similar, but they've adapted to different functions. Look how they eventually, it's similar structures. Just look at the whole thing, the whole structure. This one here developed into fingers, of course, and a hand, but this one into claws and paws. This one into a wing, and into a flipper. For the whale, it's a flipper, and for the bat, it is a wing. But either way, it's very similar structures. And then, moving on now, You are more than welcome to contact me for more clarification or for me to provide you with this worksheet if you need it and the instructions on how you can do it on your own. I can also try in the next lesson, try and let's us watch videos of these structures as well. Evidence from observed natural selection. Now we're moving on to that. Examples of evolution are found in many everyday phenomena. For example, antibiotic resistance and lactose intolerance in humans. Those are evidence of natural selection. And then now, there is a difference between a hypothesis and a theory. We need to test those differences. Is evolution a fact, a theory, or a law? That's what we need to explore. Those are the questions we need to ask as we're moving on with this. What is meant by a fact? A fact can be defined as a statement that is accepted as being true because A, to substitute it with a statement of opposite meaning would be absurd and would violate common sense. Yeah? So if you have a fact and then you give it, you substitute it with a statement with the opposing meaning of you, that would be absurd, it would be crazy, it would violate common sense. Then B, the statement is verified by many observers. This means that a fact should be readily observable and measurable, regardless of the person taking the observations. So that's what you can do. This fact should be readily observable and measurable. So before you can say something is a fact, it should be readily observable and measurable, regardless of the person taking the observations. And it means it should make common sense. So observable will mean that that can be seen in the environment. You can see it. You can clearly, if you say what can I say? If I can say what oranges are orange, you can clearly see that. You see it. It's orange. You know, if someone were to say oranges are black, then that would violate common sense and it would be absurd to go against the fact that oranges are orange, you know. And then measurable, you can collect as many oranges as possible. Go around many trees, orange trees, and see if you'll ever find a black orange. You understand? So measurable is that fact. It can be quantified, not only described. That's what I mean. You can go around counting as many different oranges to prove that fact. Another example here, you can say the tomato is red. Is this a fact? Yes. Many people who see the tomato can testify to the tomato's color. You've seen tomatoes. When it's ripe, it's red. But what if the observer is colorblind? What if you're saying now you have a sample size, you have people who are there to observe, and there are people who are colorblind and they're saying, no, this here is not red. That then can be very difficult and tricky to define as a fact. Ne? So that is a tricky thing to do. Other facts, the dinosaur femur A is 1 meter long. Dinosaur femur B is 2 meters long. These facts here only tell us what is. They do not tell us why that fact is or what it means. Same way when we speak of the orange, the tomato is red or orange is orange. I'm merely just telling you what is. You are also observing what is. What you see and what you can observe and measure doesn't really explain why it is the way it is. We are just stating a fact. The tomato is red. So you are not even trying to, you are just stating a fact. That fact is not meant to explain why the tomato is red. It's mainly a fact that you're looking at it and it's red. And it's not meant to tell you what that means. It's basically just an observation and a measurement that it is red. Same with the information here. Dinosaur femur A is 1 meter long. Dinosaur femur B is 2 meters long. These are facts. Why it is like that or what this means has nothing to do with it being a fact. As long as it's observable and measurable, it makes it a fact. So you need to understand those. Other facts which we've already discussed here. There are similarities in the forelimbs of mammals such as human, cats, whales, and bats. That is true. We've seen it. We've seen it in this diagram here. We've seen it. There are similarities in the forelimbs of these four species, right? We've seen it. And then We've also, you can observe and compare the humerus, radius, ulna, carpal bones, metacarpal bones, and phalanges of the different animals. We have observed them and we have compared them, all of those ones. We've seen them, we've compared them, and we've seen, we can clearly say for a fact, they are similar structures, and chances are, you know, it's a fact, they are similar, they have common, there are similarities. The fact of the matter is that there is a similarity. We've seen it, we've compared it, and it's a fact. That's what you've seen, that's what we've measured. It's a fact. There are similarities in the forelimbs of mammals such as humans, cats, whales, and pets. And we leave it at that. It's a fact. Why it's like that, what that even means is another topic on its own. But as for a fact, yes, it's a tick. That is a fact. And then, however, now, if we now interpret this information and use it to prove evolution, we are speculating, we are formulating a hypothesis, or defining a theory. And what are the differences between these things? So we've deduced the fact. Né? That's how you do your own research when you're a scientist, really. That's how you go about it. You observe things, you measure them, and you see it as a fact. Once you've ticked that block that this is a fact, you've ticked that. Then to prove, to find exactly what that means and why it is like that, you can then go on whereby you will speculate, you will formulate a hypothesis, define a theory, test it to prove it. Because now you've stated, you've proven that it's a fact, right? We agree it's a fact. But what are the differences between these things? What's the difference between a theory, hypothesis, speculations? What are those differences? A speculation is calculated, logical, and rational theoretical explanation of a fact with no testing to verify or disprove the idea. So when you make a speculation, it needs to be calculated, it needs to be logical and rational, it needs to be theoretical explanation of a fact with no testing to verify or disprove the idea. So before any testing is done to either verify or disprove that idea, it needs to meet the fact that it needs to meet the criteria that it needs to be calculated, logical, rational. It leads to explanations of models that can be broken into testable pieces and eventually confirm or reject or modify the original speculated model explanation. So models, remember that question about models? They are mainly speculation based on calculated information we have, and it makes logical and rational sense that we would make that assumption of the model or make that design of the model. It is a speculation though. It can still be tested to either accept or reject it. And that's why models are continuously tested so that they can either be improved or rejected completely as time goes by, right? But it is a speculation. A hypothesis though, a hypothesis is an explanation with some evidence behind it. Testing and experimentation have been done. So when you bring forth the hypothesis, now you have evidence. You're not just speculating. There is evidence behind it, meaning you have tested it and you have done experiments. And then now you can clearly say, yes, this is a hypothesis because there's testing and experimentation that have been done. When you do an assignment or an experiment and you provide a hypothesis, the other steps there would need you to show various steps of how you are conducting this experiment to prove or test your hypothesis. After you've tested your hypothesis, you can either accept it or reject it still. To test the speculation that B evolved a longer femur than its ancestor A person must first provide evidence that B evolved from A. So you see, you need to provide evidence. Remember these femurs, the dinosaur femur A, dinosaur femur B. These ones here is 1 meter long, dinosaur femur B is 2 meters long. Now to test this, like we're saying here, to test this speculation that B evolved a longer femur than its ancestor A, you must first prove that indeed A is the ancestor of B. That's then the hypothesis. And then a theory. A theory is an explanation with a large amount of evidence and testing behind it. We are running out of time now. We'll continue from tomorrow. I'll sum it up from the first, the speculation, and then we'll continue from tomorrow. But the topic, the work here is from Via Africa, grade, trying to go to the end. Via Africa, grade 12 learner's book, and I accessed it from Snaplify app. So do yourself a favor, go get the app, download as many books as you need to assist you with your studying and your work. For more information, www.africateengeeks.co.za. Don't forget, next week on the 29th, it's an assessment for life sciences. Sign up on the website so that you can get access to the paper and you can be able to write, to test your progress, to see exactly where you stand with the work. Remember, you are still writing exams on the whole curriculum, guys, so please prepare yourselves. Make sure you are ready for this work. Ne? You need to do well. I want you to do well. It will cover term 1 and term 2's work. For more information, you are welcome to also send me an email and I will assist you. Thank you so much, everybody. Bye.